Welcome to the Arc Reactor. This is our first ever video, where we'll dive deep into fascinating topics at the crossroads of science, technology, and geek culture. Today we're going to break down the physics behind one of the most scientifically complex movies of our time, Interstellar. If you haven't seen the movie yet, I highly recommend you watch it first before we dive into the science behind it. And don't forget, you can check out our other content on black holes to prepare for this cosmic journey. You ready? Let's go. You knew this, right? First, let's clear up any doubts about the movie's storyline or the emotional twists. No matter what you think about its plot, Interstellar stands as one of the most scientifically accurate films ever produced. Thanks to the contributions of Kip Thorne, a renowned physicist specializing in relativity and gravitational theory, the science woven into the script is truly extraordinary. Kip Thorne has collaborated with some of the greatest minds such as Stephen Hawking and Carl Sagan, which explains why the physics in Interstellar is so well-founded. Now, let's put aside the film's antagonist, the blight that ruins crops and depletes the atmosphere's oxygen, and talk about how physics saves the day. The whole film revolves around Einstein's theory of general relativity. One of Einstein's brilliant insights is that space and time are not fixed. They can warp, creating the force we perceive as gravity. A historical example of this was demonstrated during a solar eclipse in Sobral, Brazil in 1919, when scientists confirmed that the sun's gravity bent starlight. One key experiment that showcases how gravity warps spacetime took place between 1976 and 1977 with NASA's Viking 1 and Viking 2 probes. These spacecrafts orbited Mars, sending radio signals back to Earth. Researchers noticed that when the sun was positioned between Earth and Mars, the signal took slightly longer to travel the same distance. This confirmed that the sun's gravity distorts spacetime, slowing down the signal. We live in a four-dimensional universe, 3 dimensions of space and 1 of time. When traveling through these dimensions, just like the TARDIS from Doctor Who or the DeLorean from Back to the Future, we need to know both where we're going in space and when we're going to get there. As Neil deGrasse Tyson explained regarding Interstellar, to meet someone you need both spatial coordinates and a time. Michio Kaku likens this concept to objects interacting with the surface of water. Massive objects like black holes deform the fabric of spacetime around them, which gives rise to phenomena like wormholes. In Interstellar, the crew uses a wormhole to travel from our solar system to the system of the black hole Gargantua. But Christopher Nolan, the director, didn't just stop at theoretical explanations. Kip Thorne gave detailed equations about how the gravitational field of a black hole would distort space. This data was provided to the movie's visual effects team, led by Paul Franklin, who worked on Inception. They used Thorne's calculations to create some of the most scientifically accurate visual simulations of a black hole ever seen in a movie. That's why Gargantua, the black hole in Interstellar, looks so unique. In most portrayals of black holes, we see a flat accretion disk, material being sucked in much like Saturn's rings. But in the movie, spacetime itself warps around Gargantua, creating a gravitational lens that bends light around it, forming a halo. This same accretion disk illuminates the nearby planets, like the water-covered world of Miller and the frozen world of Man. One of the most mind-bending aspects of Interstellar is the time dilation that takes place on Miller's planet. According to Einstein's theory, time moves more slowly near massive objects. In the movie, 1 hour on Miller's planet equals 7 years back on Earth. For this to happen, the planet would have to be orbiting incredibly close to Gargantua, at 55% the speed of light, creating immense gravitational forces. In fact, the planet would need to be so close to the black hole that, in reality, it would likely be ripped apart by tidal forces. Speaking of those forces, the extreme gravitational pull of Gargantua would create tidal waves similar to what we see with the moon's influence on Earth's oceans, but on a much larger scale. The kilometer-high waves seen on Miller's planet are scientifically plausible under these conditions. Thorne calculated that Gargantua would need to be at least 100 million times the mass of our Sun and spin almost at the speed of light for the events in the movie to occur. This rapid rotation helps explain why Cooper, the protagonist, was able to survive after falling into the black hole, thanks to a phenomenon known as frame dragging, which lessens the extreme forces he would have otherwise encountered. Now, while the science in Interstellar is rigorous, there are still artistic liberties taken. For example, the events that take place after Cooper enters the black hole, such as the Tesseract and time manipulation, are speculative. As the film emphasizes repeatedly, nothing can escape a black hole, not even light. Yet, within the movie's universe, the rules about gravitational waves and time travel are internally consistent and make for a thrilling story. One of the most intriguing aspects, according to physicist Michio Kaku, is how Interstellar uses the concept of wormholes not just for space travel but for sending information across time. The scenes involving Cooper communicating with his daughter through gravitational waves offer a creative twist on the notion of causality and relativity. In fact, Interstellar plays with the idea that while light and matter may be trapped in the confines of a black hole, gravitational waves could, hypothetically, traverse both space and time. Although it's still a product of creative license, the idea is based on current theoretical physics, making it a fascinating topic of discussion for science enthusiasts. While the movie leaves us with plenty of unanswered questions such as what really happens inside a black hole, Interstellar remains one of the most scientifically ambitious films of our time. The combination of real physics with a thrilling narrative ensures that it will continue to inspire curiosity about the mysteries of our universe. Thanks for watching. We hope you enjoyed this deep dive into the science behind Interstellar. If you're as fascinated by the cosmos as we are, make sure to subscribe for more tech, science, and geek content. You knew this, right? See you next time on the Arc Reactor. And don't forget to hit that like button and share with fellow space enthusiasts.